Good day, everyone. My name is Leo Wei, and today I will be presenting my project on the design and analysis of an amplifier with an active load supervised by Professor Cao Changpo. So, in this project presentation, I will be cover the following, which is the elaboration of the circuit, the schematic and design, the simulation results, which in this project I will use HPICE, discussion of questions and conclusions. To start, let's understand the motivation behind using an active load. As traditional amplifiers often use resistive loads, but in IC design, large resistors take up space and can limit performance. By using MOSFETs in saturation as an active load, we get a high output impedance which improves gain and frequency response and also saves chips area. This project uses the cascade configuration which further improves gain and stability. The cascade circuit structure combines the high gain of a cascade configuration with the high output impedance of an active load, such as current mirrors, which allows the circuit to possess a high voltage gain, improve in output swing, better frequency response, and also where analogically the voltage gain will be as stated is as in this slide here. And this is the circuit schematic configuration where on the left side is the OP and the right side is the current generator. Combining those two, we will have a complete circuit as follow. And combining and also this is the DC gain and F3dB and also the non-nominal pole and voltage gain. All of those values is obtained here by the complete circuit before. And this is the overall schematic of the amplifier. The core of the circuit includes a differential input stage, a folded cascade stage, and also a current mirrors to form the active loads. The differential pair consists of M4 and M5, while the M6 and M7 are used to fold the current into the PMOS load path. M9 to M12 mirrors the current and direct it to the output of VO positive and VO negative. The current generator section bases the entire circuit using M1 to M14. In more detail, the cascade stage formed by M9 to M12 plays a critical role in boosting gain and improving output swing. The folded structure allows us to use NMOS inputs while still maintaining high gain by redirecting current through PMOS mirrors. This design also improves the common mode rejection ratio or CMRR, which is an important metric in differential amplifiers. So this is the designing procedure where phase one is to understanding the specification given and also move on to phase two is the initial design and phase three is the final adjustment towards the design. This is the standard of our design where every MOSFET should meet the saturation region, which is both here on on the very bottom of the table. By following the specification, we could conclude a voltage and current values for the MOSFETs as follows. And continuing on phase two, we will continue to simulate all of the sizes, width and length for each MOSFETs. This is the example of the result where 1.5 micrometer is the width of the MOSFET where we assume the length of the MOSFET is 1 micrometer. This is the result of the DC simulation where we check for each region of each MOSFET, which is blocked here on the red boxes and also here. After confirming in the right region, we could continue to simulate the gain. Where in this, we could see that the gain is out of the specifications. Therefore, we have to adjust the sizes or the current to meet the specifications. To remind you, our goal is to obtain the following specifications. After some tuning, this is phase 3, where this shows the output voltage on the red boxes, and this is the unity gain frequency or the UGF. Next up is the DC gain. This is after we tune up the specific tune up the circuit to meet the specifications. And lastly, the F3dB, which marked here on the red box on the bottom, which is point to 4.54 megahertz. These results have been obtained by tuning the sizes of M4 and M5, and also modifying the tail current provided by M3. An important consideration in the design was how the device ratio between M9 and M10 and also M11 and M12 affect the performance. Adjusting this ratio changes how current is split between VO positive and also VO negative, which can create an intentional offset or symmetry. Match ratio gives balance gain and high CMRR, while mismatch ratio may degrade precision. The figure of merit calculated was 275.6 MHz over milliwatt, which reflecting a good efficiency. And to conclude, this project demonstrates the importance of both theoretical and knowledge of simulation in analog IC design. The cascade with active load structure help us to achieve high gain, wide bandwidth, and efficient layout. Through this project, I also gained valuable experience in designing from scratch, debugging, and also understanding the impact of each transistor's role. And that is all from me. Thank you to Professor Zhao Changpo and Alan Chen for their support and guidance, and thank you for listening to this project presentation.